Chapter 11.4, Day 1, we're looking at lines and planes in space. We're going to find parametric and symmetric equations of lines in space and find equations of lines in space. Lines in space. In the plane, slope is used to determine an equation of a line. In space, it is more convenient to use vectors to determine equations of lines. In the figure below, consider the line L through the point P, x1, y1, z1, and parallel to the vector v of a, b, c. The vector v is a direction vector for the line L, and a, b, and c are the direction numbers. One way of describing the line L is to say that it consists of all points q, x, y, z, for which the vector pq is parallel to v. This means that the vector pq is a scalar multiple of v, and you can write vector pq equals t times v, where t is a scalar. So vector pq, to find that, you're going to take the terminal point minus the initial point. So x minus x1, and then y minus y1, z minus z1, which ends up being a times t, b times t, or c times t, or just a scalar tv. So just a little bit of background on it, but we'll get some practice on these. Now, by equating corresponding components, you can obtain parametric equations of a line in space. So this is what we're going to use. A line L is parallel to the vector v of a, b, c, and passing through the point P is represented by the parametric equations. We have x equals x sub 1 plus a times t, and y equals y sub 1 plus b times t, and z equals z sub 1 plus c times t. So this is what we are going to use. When the direction numbers a, b, and c are all non-zero, so notice that, when a, b, and c are non-zero, solve each parametric equation for t and set the resulting expressions equal to each other to find a set of symmetric equations of a line. So these are our symmetric equations, and so these are the equations that we'll use. So we'll use that in our first example. Example 1. Finding parametric and symmetric equations. Find parametric and symmetric equations of the line L that passes through the point 1, negative 2, 4, and is parallel to the vector v equals 2, 4, and negative 4. So this point here, we'll call this point P. So this is x sub 1, y sub 1, z sub 1, and then the vector v, we'll label this as a, b, and c. So what we're using for our parametric equation, so I'm just going to write it here, parametric equations. We're using the x equals x sub 1 plus a times t, y equals y sub 1 plus b times t, and z equals z sub 1 plus c times t. So we just plug in what we know. So x equals x sub 1 is 1, plus a is 2 up here, and then times t, so 2t. Then y will be y equals y sub 1, which is negative 2, plus b, which is 4, times t. Z equals z sub 1, which is 4, plus c, which is negative 4, times t. And then you could, of course, simplify that. So z equals 4 minus 4t. So these are the parametric equations. Next, we have to do the symmetric equations. So remember with these, we're looking at x minus x sub 1 over a equals y minus y sub 1 over b equals z minus z sub 1 over c. So our x and y and z here will stay. That doesn't change. So we're just plugging in our x sub 1 and our a. So this is going to be x minus x sub 1, which is 1, over our a value of 2. And then that equals y minus y sub 1, so minus a minus 2 right here. So that'll be a positive 2 over b, and b is 4. Then we have z equals minus z1, so that is 4, so minus 4 up here, and then all over negative 4. Okay, and then so that is our symmetric equations. So try out these examples here. Find the parametric and symmetric equations of the line L that passes through the point 2, 1, and negative 3. So if you tried this out, you would find the parametric equations to be x equals 2 plus 4t, y equals 1 minus 2t, and z equals negative 3 plus 7t. The symmetric equation was x minus 2 over 4 equals y minus 1 over negative 2, and z plus 3 over 7. Now, just as a note to talk about this, neither the parametric equations nor the symmetric equations of a line are unique. They're not unique. For instance, in example 1, if we let t equals 1, so go back to example 1, if we let t equal 1, we plug that in, that will yield another point. So if we plug in 1 to each of these, we are going to get 3, 2, and 0 on line L. Then using that point with the direction numbers with A of 2, B is 4, and C is negative 4, so what we had initially up here, right up there, it would produce the parametric equations x equals 3 plus 2t, y equals 2 plus 4t, and z equals negative 4t. So just as an FYI, just wanted to talk about that.